to Juliet and Tess for running this, and to everyone for coming here. It's really nice to be here. Good to see old friends as well and stuff, so hi everyone. So yeah, my name is Maurice, and I want to talk about enhanced weathering and how rocks can potentially be a meaningful solution to the climate crisis. And my company is called Silicate. So firstly, where are we with CO2 in the atmosphere? You can see behind me that we've had CO2 levels in the atmosphere fluctuating for a very long time. They've been very high, they've been very low, but most importantly, they've been, for the last more than 3 million years, very stable, very low, kind of below 280 ppm, parts per million. And really, it's in the last 200 years that something happened. We started burning fossil fuels and released loads of CO2 into the atmosphere. So we've perturbed a system that was totally fine for more than 3 million years in just 200 years. So it's a pretty big achievement, but obviously not a good thing. So we've maybe got to remove some. So we know it's high, but how much do we have to remove, and do we actually have to remove it? And the answer is yes. So there's loads of different scenarios we have, to try and stop climate change, etc. The most important one is the bottom one, which you can see kind of with my dodgy pink line that I drew over the last one. And what this is saying is essentially, to stop climate change, it's 2 degrees or less. That's the critical thing. And you all know that, right? Everyone knows the 2 degree, the 1.5, these aspirational things that we have to do if we want to maintain a habitable planet, essentially. And to achieve that, you've got to remove CO2. So you can see it's going below that line, the bottom one. And that means we've got to take CO2 out of the atmosphere. So we've got a few tools in our kit to do that. And what you're seeing here is 4 different pathways, potentially. The first one, the bottom left, is nature-based. It's the most intuitive way. Planting trees, all of those good things. And it works. You can capture CO2, but there's some downsides too, like maybe additionality. You guys probably read the Guardian piece last week on carbon credits. A good few nods. Yeah, it was a big thing. So, limitations, but also good things too. So yeah, it's there. But the permanence, which is what's plotted on the y-axis, isn't that high necessarily. The next one up then is biochar. So you're basically doing one step further with biomass, heating it up to really high temperature, and you're trapping that carbon for a good bit of time. Its permanence, though, is kind of up and down. It really depends who you talk to. So again, a good solution, but probably not going to get us the whole way there. The third one, further over, direct air capture. This is using big, massive fans, essentially to suck in ambient air, strip it of CO2, and then pump it underground and store it away. Really great. Will scale for sure, but it needs loads of cheap green power. So big things there. And the last one, my favorite one, is what we do, mineralization, and yet we're using rocks, no surprises there. And how that works is what I want to try and explain, if I can, very briefly, in the time I have left. So what you see here is, does anyone know what the place is? What is it? Giant's Causeway, great, in Antrim in Ireland. Beautiful place, definitely go there. And some poor woman trying to brave the elements there with her umbrella. So the Giant's Causeway is basalt, and basalt is really good at capturing CO2. So the Giant's Causeway is actually a natural sink. It's sucking in CO2 all the time, and this is happening because of weathering, which is essentially acids attacking the rock and sucking in CO2. That's very, very simply put. But not just basalt or olivine, but concrete as well, and that's what my company does. We take waste concrete, crush it, and capture CO2. That's the gist of it. A bit more chemistry. Probably going to lose all of the room or some of the room here, but anyway, that's what it is. What I want to get from this is we've got the first thing is the acid. This is carbonic acid. It's CO2 dissolved in water, so it's a very weak acid. It wouldn't hurt your skin if you put it on, but it's good at weathering to capture CO2. The next one, here we go, is that is the mineral that we're weathering. So in our case, it's portlandite, or calcium hydroxide in the concrete from the cement. That's being attacked essentially by that acid, and the result is some calcium cations, which is good, but this one here is the critical one. It's bicarbonate. It's like baking soda. That is the store. So that stays in the soil water when you apply it to fields, and that is your store of carbon. So it's really stable. You need really high temperatures to re-release that carbon atom back into the atmosphere as CO2. So once you create it, you've stored that carbon for thousands of years. So it's an amazing thing. So when we're measuring what's happening, we're looking for that stuff. That's the gold. And a bit of H2O at the end. So enhanced weathering. Oh, the video's not working. Can we hit go on it? No? Oh, well, that's a video that should be working, showing a tractor spreading dust, essentially. It's very, very scenic. It's a shame it's not going. That was filmed. It would be filmed if it was working in August, just gone. So we spread 1,000 tons of material And this is kind of first of a kind, world scale capturing CO2 with concrete. So we're learning a lot from that. That's been really fun. We're doing 2,000 tons in a few weeks. So come to Ireland if you want to see concrete being spread in the field for real, not just on a film. Okay, so talk about how we do it, what it works. But the critical thing is how you measure, right? We've got to build trust in what we're doing. I could say we're capturing loads of carbon. You'd say, yeah, great, Maurice, well done. But I need to prove it with science. So we measure what's happening. So very briefly, how we do it. The first one is soil samples. This tells us how much weathering's happened. So we go to the fields, sample around different areas, and we bring it back to the lab and do some analysis. We learn what's happening. The second one is not working. Is soil water samples. This is where we look for the bicarbonate. So taking in water from the soil and tells what's happening. And the third one, is greenhouse gas fluxes. So very, very cool piece of kit. You put a jar over some soil and you see how much CO2 is fluxing from the ground into the air. And there should be fewer CO2 molecules in the area where you've added material. Does that make sense? Okay, some nods. Okay, good. Happy with that. So, measuring is critical and proving what we're doing is absolutely essential. Why? Because of this Guardian thing. We've got to build trust. No one's going to get involved in carbon removal or buy carbon removal credits or do anything if they don't believe what we're doing. So for Silicate, science is critical. It drives everything we do. We want to prove empirically that it works. And we have done, but we want to showcase that. Because building trust in carbon removal is essential if we want to turn this rising CO2 levels that we've seen since all of our lifetimes, it hasn't changed, into this, going down and avoiding climate change. Thank you very much.